MaxScript has a large set of features to help script animation, perhaps not surprisingly. There are many different ways you can write scripts to set up animation, including automatic keyframing, individual controller and key manipulation, setting up parameter wiring, or writing your own fully scripted controllers, and we'll explore some of them now in detail. The simplest way to script animation corresponds to the simplest way you do animation in Max, namely turning on the auto keyframe mode, setting the time slider, and manipulating objects to automatically plant keyframes. MaxScript has virtual equivalents of the auto keyframe button and time slider that you can use to do the same thing in a script, and it'll capture any changes you make to objects in the script as keyframes. Okay, here's a scene with a ball on it, and here's a script to animate it. The Animate On here turns on MaxScript's virtual auto keyframe button for the duration of the expression following it, in this case the code block, and then turns it off again. Any changes made to Max objects or their parameters by code inside the block will cause keyframes to be planted for those values. This doesn't actually turn the auto key button red, but it has exactly the same internal effect. In a similar way, the @time0 and @time100 here set MaxScript's internal time slider for the duration of the expressions following them, in this case code that sets the ball's position. So the first line in the block will set a position keyframe at time 0, position -100, 0, 0, and the second will set a position keyframe at time 100, position 100, 0, 0. And you can see if we execute it, the ball indeed animates between these positions. These two clauses, animate and @time, are called context prefixes because they set up a special context for any expression or block that they prefix. You can do basically anything you like inside the code controlled by these prefixes, adjusting and modifying any number of keyframeable objects or parameters to achieve the animation effects you need. Here's another example using a loop to plant a series of keyframes at different times. I've created up here another sphere in the scene, which I've grabbed into the variable b2. I want to animate it so that it follows the original ball across the xy plane, but tracks randomly around the main ball as it goes. And additionally, I want to make the radius of the main ball pulsate in a sine wave pattern. So let's run it first, start the animation. You can see the small red sphere now randomly following the large ball, which is pulsating as desired. If we look at the track view, you can see the small sphere's position curve shows a random walk modulating a trip across the x-axis from -100 to 100, with keyframes every 5 frames. And the big ball's radius is a sine wave, again with keyframes every 5 frames. The Animate On clause here sets up a prefix context for the entire loop, so any object changes inside the loop will generate keyframes each time around the loop. The loop runs a variable t from 0 to 100 by 5s, which I use to set the time for each set of keyframes by prefixing the loop body with an @time_t clause here. The first time around the loop, the @time is at frame 0. The next loop, it is at frame 5, then frame 10, and so on. This makes any keyframing inside the block happen at those times, and equally importantly, causes any object property accesses to be also evaluated at those times. I need this so I get the correct position of the main ball at each keyframe to base the tracking sphere's position on. So this line will set B2's position to the main ball's position at the context time plus a random vector. I'm using the built-in random function here, which takes a low and high value and gives you a random value in between. Setting the position inside the Animate On plants a position keyframe as we want. The next line keyframes the main ball's radius using a sine function of the time variable. As I mentioned, the @time context sets the internal time slider for the evaluation of its following expression or block. You can use this prefix on its own, outside of an animate prefix, say to do across-time calculations. In this example here, I'm getting the ball's position at time 10 into the variable P1, and here at time 50 into the variable P2, and then computing the distance between those points here using the distance built-in function to tell me how far apart the ball's positions are at times 10 and 50. Note that a prefix like this just sets the context for an expression. The overall expression still yields its value as always. So far, the time has been given as an integer, which is always taken by MaxScript to be a frame number. There is also a general-purpose time value class which lets you specify times more or less arbitrarily, and that can be also used in time prefixes. Here are some of the ways you can write time values in MaxScript. An S immediately after a number means that this is the time in seconds. An F says this is the time in frames, and they can be fractional as well. A T specifies ticks, which is the smallest time unit inside Max. There are 4800 ticks per second, the internal Max time resolution. You can string M and S and F suffixes together to give you minutes and seconds and frames. Or you can use the standard SMPTE notation for minutes, seconds, and frames. All of these can be used as time literals in MaxScript. And you can use them to write things like this, a loop which will print the ball's position at 1/100th of a second intervals by using the time value here in the loop range and increment. Time values are particularly useful when used like this for wall clock time or subframe animation scripting. The final things to mention about animation contexts are their nesting and scope characteristics. We've seen in a simple way that contexts can be nested. In all the animation samples so far, I've nested at-time contexts inside animate-on contexts to control the keyframe timing. You can also nest contexts within themselves, and when you do this, they save and restore the context that was in place around them. In this example, I'm animating the radius of a moving ball based on the distance in x between the ball's current position and its position at time 0. The outer at time is setting the time context for the entire block, but this nested at time will override the outer at time just for its following expression to get the ball's position at time 0 and then restore the outer time context so that the radius keyframing and the current position access use the outer context's time. All contexts work this way. If you nest them, they will save and restore the context that was in place immediately surrounding them. The other special thing about contexts is that they have what is known as dynamic scope. This means that any code that runs while the context is in place is controlled by that context, including code in any functions that are called or any that they call, and so on, even including any of MaxScript's built-in functions. Let's look at a slightly less trivial example to demonstrate this, and while we're at it, some useful techniques for working with splines. Okay, here's the task. I have a scene with two splines weaving through space, forming a pair of rails. I also have a thin box on its side that I want to animate along these rails such that its ends track along the rails as it moves, and its length adjusts to fit exactly between the rails. Here's the script. Again, let's run it first. Okay, as I twiddle the time slider, you see the box tracking along between the rails as desired. I've broken the script into two parts to make it easy to think about. A function up here that will do the box placement at a given offset along the rails, and this keyframe animation loop down here that drives the whole thing. In fact, I've written the function without any animation-specific code at all. It simply places the box on the rails at some point, and could potentially be used in other scripts that don't do any animation. The key point is that its use for animation is determined by the animation and time context set up by the code that is calling the function, demonstrating this notion of dynamic scope. Let's look at the main loop first. It's a conventional keyframing loop prefixed with animate on. The time bounds are set in these two variables, start and end, and in this case I've loaded them up from the system global variable animation range, which contains the active time segment for the scene. Working with splines in MaxScript often involves specifying a fraction along the line, similar to the percentage parameter in the Max path controller. This is called the interpolation parameter, and it's always in the range 0 to 1.
The rel_follow function call here takes just such an interpolation parameter to specify where along the splines to place the box. Since I want the box to be moved along the line as time increases, I compute this parameter from the loop's time variable, here figuring t as a fraction along the animation range. I had to convert the time values to floats here, since you can't divide time values, and you want the result to be a floating point number anyway, not an integer. Finally, I called the rel_follow function, giving it the box to place, the two lines to use as rails, and the interpolation parameter in the local variable u, prefixing the whole thing with an @time t to set the time context for the call to the rel_follow function. Both the animate_on and the @time contexts are in force when the function is called, and because of dynamic scope, they remain in force whilst the function is executing. This will cause any object changes inside the function to plant keyframes, so we should get position, rotation, and sizing keyframes every 2 frames, as each repetition of the loop places the box farther along the rails. Okay, let's explore the rel_following function. It takes as parameters the object to place, the 2 rail splines, and the spline interpolation parameter, by convention in a variable named u. I actually have a simpler version of the function to look at first. It's the implementation I first thought of, but it gave slightly odd results, and I wanted to explain how I improved it. The main trick here is the use of the built-in length_interp function. Given a spline and an interpolation parameter between 0 and 1, it returns the 3D position of that offset along the spline. I use this function to get the offset points along both splines, corresponding to the given interpolation parameter. I figure the direction vector from one point to the other, calculate the distance between them, and then use all these to place and orient the box. So here I get the positions on the rails into P1 and P2 using the length_interp function. Then do a vector subtraction to get the direction vector from P1 to P2 and store that in variable dv. And then I use the built-in distance function to get the distance between these 2 points into the local variable d. Then to place the box, I position the pivot end at P1, set its local z direction so it points at P2, and adjust the height so that it covers the distance between the points. Sounds good? Let's run it and see why it gave wonky results. You can see that at around frame 20 here, the left-hand side is lagging noticeably. It also happens for the other end at around frame 75. The reason for this is because the rails are different lengths, and so a particular offset along one rail is not directly opposite the same offset on the other rail. Notice here that the rail bulges out, and so it's definitely longer here than the other rail. Now what I'd wanted was for the box to lie perpendicularly across the 2 rails as it moved. So I fixed the script like this. I chose one rail to move along with length_interp as before, but then used another very useful spline function, nearest path param, which takes a spline and a point in space not on the spline, and gives me back the interpolation parameter corresponding to the point on that line closest to the given point. By doing this on the second rail, using the length_interp point on the first rail, I got the parameter on the second rail closest to that point into the variable u2. Then I fed that parameter into a path interp on line 2 to get the point on line 2 closest to the original point on line 1, and then used those points as before. Okay, let's run this again. And now you can see it works much more as desired. Note that I keep running these scripts on the same scene. Each time it runs, it simply updates the keyframes that were placed there in a prior running.
Well, I won't claim this is all trivially easy, but the spline functions can be really useful and are well worth experimenting with.